So good evening. On behalf of the Institute Colloquium Committee, I would like to welcome all of you today to this Institute Colloquium by Dr. Santosh Ansumali. It's titled Drik Ganit Towards Realistic Simulation of Complex Systems. Before we begin, I would like to request all of you to kindly switch off or keep on silent mode your cell phones. Thank you for that, and I would also like to welcome all of the online participants who are attending this Institute Colloquium. I would like to invite Professor Chaudhary to welcome Dr. Santosh Ansumali with a bouquet. Thank you, Professor Chaudhary. It's my pleasant responsibility now to introduce the speaker for today's Institute Colloquium. Dr. Santosh Ansumali is a professor at Engineering Mechanics Unit at the Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. He is also the founder of Sankhya Sutra Labs, Bangalore, and was its CTO in the year 2019 to 2021. Before his stint as a professor at JNC ASR, Dr. Ansumali was an assistant professor between 2005 to 2009 in the Department of Chemical and Biomedical Engineering at the Nanyang Technological University, Singapore. He did his BSc in Chemical Engineering from the Bihar Institute of Technology in 1998, his ME in Chemical Engineering from the Indian Institute of Science, Bangalore. In 2000, he received his PhD from the Institute of Polymer Physics, Department of Materials, ETH, Zurich in 2004, and completed his postdoc from the Department of Energy Technology, ETH, Zurich in 2005. Dr. Ansumali's research interests include mesoscale simulation methods, kinetic theory, and high-performance computing. In particular, his focus in the last decade has been on the development of entropic lattice-Boltzmann method for the simulation of fluid flow. This formulation is regularly used in commercial as well as popular open source codes such as Palabos and OpenLab. His group has helped create a large-scale code for direct numerical simulation of hydrodynamics using the lattice-Boltzmann method. These efforts have led to the creation of the Sankhya Sutra Lab and its multiphysics simulation platform. His work in COVID-19 research and planning was an important starting point for India's supermodel for COVID-19. Dr. Ansumali has several awards. He is a recipient of the CNR Oration Award 2022, the APJ Abdul Kalam HPC Award by HP Cray in 2020, the Ramanujam Fellowship in 2009, and ETH Gold Medal in the year 2004. What's more special to us at IIT Bombay is that he is the first ever recipient of the IIT Bombay International Award for Excellence in Research in Engineering and Technology, which was conferred on him just yesterday. With those words, I would like to invite Dr. Ansumali Santosh to kindly deliver the Institute Colloquium.
Can I start? Yeah. So first of all, I would like to thank Professor Chaudhary, to give me an opportunity, and IIT Bombay in general, to give me an opportunity to be here, speak, and for this honor. I am highly honored to get this award. So, as the professor told, I am a faculty at Jawaharlal Nehru Center for Advanced Scientific Research, and at present I wear dual hat. I am also one of the founder and of Sankhya Sutra Lab. So what I will do in this talk, I will talk about little bit about my research group and the kind of philosophy we have, what is the thought process we work with. Then I'll describe a little bit about the Sankhya Sutra and the kind of thing we do, the actual technical problem, the philosophy we had, why we started this startup, and some of the issues I will try to raise, technical as well as what we feel is difficulties in deep tech companies in India. So I begin with this small simulation of a quadrotor and one car simulation. So these are standard uses. Most of the mechanical engineers or aerospace engineers would be here for the why computational fluid dynamics is useful. So many of the devices get designed with these simulations now on a regular basis. As a group, we call ourselves as a Mesoscale Lab at JNCSR. We are situated in engineering mechanics unit. And what we love is algorithm coding, what we call mesoscale methods. And we often are looking for tracking invariant manifold in various ways. Even our COVID initiative was related to that. So what I mean by invariant manifold is there are many physical systems which would have multiple timescales. And often, as an engineer, we are not interested in the fast timescales. We are interested in the slow timescale. Traditionally, search for slow timescale is done analytically, but we would like to probe that computationally. So these are the things we try to do. As tool, we have focused over last decade or so in my research group and in my research career for the last 2 decades. As a tool, I focused on lattice Boltzmann. We are interested in structured integrator in general. By structured integrator, what I mean is if it's a conservative system, we are looking at solvers which has property of preserving Hamiltonian or other thing. Similarly, we are interested in dissipative systems often as an engineer. So as a dissipative system, I am interested in solvers which build the discrete thermodynamics at the solver level. So here we want to break the traditional hierarchy of work division, what we have in the scientific computation, that a physicist will write the model, a mathematician will discretize it, then a computer science or mechanical engineer will implement it, and then mechanical, aerospace, and chemical engineers will analyze the result. So what we are trying to do is reverse that. We create discrete models which are equipped with the physical properties, conservation laws, laws of dissipations, and so on. The ultimate aim is to create a digital twin, I would say. I will little bit upon what digital twin we mean. And these also are used for our translational effort. So we had our first startup called Sankhya Sutra Lab, which has taken most of these research towards the practical code, which can be used for industrial solver. And recently we have started another startup with Dr. Divakar at Engineering Mechanics Unit called Rugna Vilekha, and that is essentially in devices. We are trying to make a PSA plants, miniaturized version of PSA plant with that. So I will not talk about that effort. Just to briefly highlight the kind of philosophy, physics-driven modeling effort we do, I'll just present one technical work we have done, which more like a fun project for us, how to generate random numbers. Most of the computer scientists will tell us this is a settled field. We do know, most of us use random number generator from the computer library. In some sense, pseudo-random number, random number on computer is a bit of misnomer, and that's why we call it pseudo-random sequence. So essentially, we need an algorithm to compute something which we call random. So that's why this word pseudo is used there, that we want a sequence which behave like, which statistically look like a random sequence. So one of the simplest way to generate is this sequence. there is a lot of research which has gone into designing good random numbers or bad random numbers. So I've given two examples. Depending on the parameter, one is a good random number generator and one is a bad random number generator. Here I've shown scatter plot of xn, means nth random number, and xn plus 1. So you can see that in one case you can see the structure, and that's a first visual indicator that the random number generator is not good. What we want is no pattern. And this field is well settled. One of the most advanced method is so-called Mersenne twister, which generate close to 1 billion random numbers a second on a typical desktop or so. But this advancement has just two limitations. One, it works very nicely for uniform random numbers, but many engineering and physics or even biology applications, we are not interested in uniform random number. For example, if I'm probing a rare event, I would be looking at random number which is sampled from exponential statistics or Poissonian statistics, or if I'm doing some molecular dynamics simulation, I would be interested in sampling from Gaussian statistics. And the second problem, and these random number generators, where I'm not interested in uniform, are not so efficient. Second problem is parallelization. Parallelization is still, I mean, we have working codes for the parallel random number generators, but still it's a challenge. Just to give a brief idea, typically non-uniform statistics is generated via some mathematical transformation. Here I've shown a mathematical transformation often used for generating Gaussian random numbers. So what you do is you generate two uniform random number and use this complicated looking formula. For our purpose, what is important here is that you need to evaluate 3 library function. And use of 3 library function means it's going to be expensive. While uniform random number, you can generate it in 5 to 10 floating point operation. This typically goes up to 200 floating point operation. And parallel stream is again an issue. So this problem, the way we looked at it, and this is what we try to do often, and we try to look for a physical solution for it. Can we create a faster random number generator from a physical model? And here we zoomed on to thermodynamics. In thermodynamics, what is known as Maxwell-Demon. So it's a standard paradox to explain the second law, that let's say there is a Demon, which there is a partition, one side, you have gas at both sides. So some of the molecules will have higher temperatures or higher kinetic energy, and some of them would have lower kinetic energy. And this guy just look at the molecule and let it pass. So if this is actually a working device, then he should be able to separate. And that would be a violation of second law. And that's used as a standard teaching paradox in thermodynamics to explain second law. That essentially he has all the information, and that information is typically a premium. He doesn't have, in practice, we won't have all the information about the system. So we would like to use this as a random number generator. So this was done by a master's student, Samarth, and was held by Soumyadip, who was working in the startup. So the key thought process we had, suppose if we have a computer model of Maxwell-Demon, it's a perfect random number generator. If we look at a molecular system and sample different property of the gases, I can, depending on the property I'm sampling, I will be able to get different kind of statistics. For example, 12th class physical chemistry will tell us that molecular velocity would have Gaussian statistics. Position will be uniformly distributed. If I draw a cell, particle number will be Poissonian distributed. If I look at a 2D cross-section of the energy, that would be exponentially distributed. And that, so the main point is a molecular system. So if I'm doing a computer simulation, computer is like a Maxwell-Demon of a molecular system, and that should be able to generate all possible random number. And with this thought, we tried all possible kind of molecular dynamics, and we zoomed on to a simplified algorithm, which I would not get into detail. But at heart of this algorithm was the fact that if I want to generate equilibrium, all I need is detailed balance in the molecular system. So I can work with a very simplified molecular dynamics. And that's the idea we would often keep coming back to, that you use a very simplified molecular dynamics which obey the conservation law and all the possible symmetry. In this case, our algorithm is pretty simple. You take a box, divide it into different cells, and let them advect, pick a pair, rotate randomly in the relative velocity. And that would be sufficient to generate the equilibrium configurations correctly. And this end up giving us random number generators which are order of magnitude faster than any conventional random number generator. And what's nice is we will get many kind of statistics. And all of this is parallel. It could have lots of practical applications. We're trying to explore on it, but we have not looked at it from the practical point of view. This is more, was a fun project we did, but this is the kind of ideologies we use in our research. Now, coming back to the Sankhya Sutra lab, so many of the algorithms, which I'll come to the algorithms we use a bit later, but just to tell about the startup, Sankhya Sutra lab. So this was our effort to commercialize all the codes which were developed in my research group. And this company was founded in 2015. In 2017, we were lucky enough to get our first industrial project from a Japanese semiconductor firm. So we did a customized design of a particular equipment. We are not allowed to talk about them. With that, we kind of survived. We had initially some small funding, and once we had this project, we could grow. And at some point, we got the investment from Reliance Group, which allowed us to essentially expand. At present, our numbers are fluctuating a bit, but currently we have around 40 members. We are happy to say that most of them are fresh graduate, either from JNCSR, ISC, or different IITs. And we have also ended up being a place where fresh PhD students or master's students are coming, doing interesting work, and then going on to different places. For example, 3 of our ex-alumni are already faculties at 2 or 3 faculties at different IITs. We have also developed with this one of the largest private sector HPC infrastructure in the country, which we call as Rudra. So it's largest in private sector HPC resource in the country, and or at least that's how ISC the top list it as, and it's the 5th largest both in private sector and public sector put together. And we use to test all our codes, and now we offer it to different companies also as a service. Another milestone we had was, and this is the kind of projects we do, this is a project with the US Air Force we are doing, where we are looking at the launch of an object from an aircraft. So it's a research project. So essentially, what you're looking at is an object is launched from this aircraft, and you are solving the equation of motion of this object which is coming out, and what you want to know is whether it will hit back or do. So it's a complex problem where you need to couple lots of engineering solution put together. So these are the kind of work we are doing in startup, and I'm proud to also highlight the kind of people we are. As I said, our staffs are of the various background, and they're coming and going. For example, Soumyadip was a fresh graduate from Institute of Mathematical Sciences. His background was BE Electronics, and he did his PhD in particle physics. Then he joined as our main software architect kind of thing. So he learned, and he did the architect of the whole thing. Now he has moved on to start his own company, and essentially in the area of animation. Punalakshmi. She was coming from one of my colleague Ganesh group. So she JNC SR PhD and then postdoc at Brown. Then she moved back to IIT Goa as a faculty. So just to highlight, Soumyadeep had physics background, Punalakshmi had aerospace background, and another is we took from ISC, who is still holding our process engineering, again a fresh graduate. So we are happy that we are able to take all these kits and get all this code development, all indigenous, both the research as well as development is largely Indian. And I'm also happy to put all the people who kind of helped here. Sunil and Nachiket. Sunil was an IIT Bombay professor. Professor Kumran, all of these people had helped. These two students of mine, who is a part of startup, they have Chakradhar and Siddharth, who had made this startup successful. All other people, my PhD advisor, and all my collaborators, with whose help I have kind of learned this field. So what we are interested in. So essentially, turbulence of fluid flow is something we see all the time in nature or engineering applications. It's still kind of unsolved problem, but what we are looking at not at the theoretical understanding, but the practical, what I would call, if I can compute the turbulence for many engineering design purpose, that's a kind of solution we are looking at. So we are looking at large scale codes which can give a shot at turbulent flow. The major difficulty here from computer science point of view is essentially, so here I've written an equation of motion from motion of fluid flow in incompressible limit. Here you have four variables, velocity field and the pressure of the fluid. The pressure does not have its own evolution equation, but there is an algebraic constraint of incompressibility that leads to pressure Poisson equation. The physics of that is sound, the fluid velocity is much, much slower than the sound velocity. So in incompressible limit, sound velocity is kind of infinite. So information will propagate instantaneously. Now, if I think it from the distributed computing point of view, it would be problematic. And indeed, it is the problem in the major problem in the computational fluid dynamics. How do you do partitioning when you have information propagating? If I take one part and it is supposed to affect other part, how do you do the partitioning? The other part is how many degree of freedoms we do need to resolve such systems. A theoretical analysis, what is known suggests that degree of freedom will scale like RE power minus 3/4, RE power 3/4 in every direction. So that would mean we have 3 dimension and the time step will also scale like delta x. So that would mean a rough computing scaling of REQ. That would mean to increase 10-fold Reynolds number, which is the only parameter in this kind of flow, I would need 1,000-fold increase in computing. And that's essentially makes the problem harder from the computing point of view. So people look for different kind of algorithm, what can be done, but what exists today is already quite mature. For example, CFD is regularly used for design automobiles. And that is pretty mature and pretty fast. The way it is done, is a methodology called as RANS, which I would say is a human intelligence rather than machine learning. So when computing was restricted, people have kind of created a database of models which works extremely well. So it's set up empirical model where you try to take any new situation and adapt to it. But even though it's good for quick searching, if you are doing a fresh design search, it has a problem. Here I've shown how it would compare with the experiment. So as engineering designs are improving, people are looking for more high fidelity methods, and that's where we have an opportunity. Now in coming to an Indian context, because startup was, we were looking more from the translational point of view. Historically, India has done pretty well in indigenization of computational fluid dynamics. For example, these were main player in India in fluid dynamics simulations in initial days, and it was done largely from a strategic point of view. Kalam, Professor Satish Dhawan, Narasimha Deshpande, and UN Sinha, when US imposed a sanction on India, they kind of even designed the processes and everything indigenously. There are n number of startup around this, used to be startup, now very mature, in RANS-related technology. There was one, GS Numerics from IIT Bombay itself. So I would say RANS capability in India is pretty advanced. And what I know, it used to be 60-70% indigenous, at least in a strategic sector. But very fast it's changing to big players. It's a big market. Computational fluid dynamics is a big market. And very fast there is a kind of aggregation. I would not say duopoly, but a few large players have survived. And here I've also highlighted one biomedical application where you have a monopoly called heart flow. The question I'm asking is, or we were asking initially is, why we don't have Indian players here? Even though we had lots of nice effort, I don't think that we even have 0.1% of the market share. Probably in this case, initial research happened somewhere else. Those were, most of these companies were outgrown from the universities. Over most of these codes takes 20, 30 years of writing. So probably it's justified that in initial days, most of the effort happened in West, so most of the companies are also from there. That kind of brings us to what we call Needham question. And I would not go into the way it is historically formulated. Needham was a British biologist who asked this question, who was also a very big expert in China. So he asked the question, if I look at India and China, they had very large lead initially in technology, maths, algorithms, and other things. Then how come modern science evolved in Pisa, not in Patna or Peking? I would not, Professor Narasimha has written a nice article on this, but I would not go in this question, but let's ask the other way around. Why even today we don't have Indian tools in science and engineering? Maybe I'm over claiming, but as far as I know, we don't have too many tools in science and engineering which are design tools coming from India. I would love to know more. And this becomes even more relevant with the successes we have in software, but at the same time, traditionally we were very strong in algorithms. One of the example which I like is almost 2,000-year-old manuscript in which was found in 1930s in Abbottabad, known as Vaksali manuscript, which is first documented use of zero, the way we do it today. But another interesting part in that manuscript was a way to compute a square root. And if you look at this square root algorithm, it's way more complex than what we often do even in a normal engineering applications. This is a quartic convergent method. Lots of modern analysis of this method is available. So essentially you do Newton-Raphson recursively to get it. We don't know how they got this algorithm, and probably it's not even relevant. But the question we have, we were traditionally quite strong in algorithms. We have a very strong software industries, but still why we don't have tools? And like to hear answers from experts. And I would say that it is more bad in the scientific areas. Scientific softwares we don't have. Probably we need to develop more and more deep tech companies to do this. Here, this article, this was further explored by Professor Narasimha at Engineering Mechanics Unit in JNCSR, who kind of argued a lot on this 1400 year of advantage and where we lost it. So I wouldn't get into that detail, but the question is, how do we create it? These are some of thoughts I have, what I feel. So maybe we have still, even with the great training we provide, still we have lack of trained manpower. We need more. Coming from research organization, I would say a continuity in research projects is almost always not there. We don't get, if you look at most of the labs in West, they have a continuity of postdocs which continue and do the thing. And that's how projects mature, but we don't have it. How to create it, I don't know the answer. Respect for labor is another part I would try to put it. And these are my views. We don't have technical cadres in most of the research universities. So you don't have good workshop, good places to get, maybe I'm wrong again, so I should this. Plus funding and hidden subsidies are also kind of lacking. One reason is scale and time of operation for deep tech companies, and by deep tech companies I meant is companies which are using research to create tools. Generally, they would have much more development time, returns are riskier, and that's understandable that very few fundings are there in India for that. This is changing fast, and Sankhya Sutra is one example where we could get a private funding to do this, but still it's low. Often such companies are built on hidden subsidies, research grant and other things. From my own experience, I would say that it's low in India. The last part, a bit controversial, I would say, maybe open source, at least in the software, open source is not doing such a good job for India. We are becoming a large user of open source software rather than developers of the either open source or closed source. We are often happy to take an open source code like in a fluid dynamics open form or something and use it and get it. There are not many people who can go around and tweak open source software to get it, to create their own open source softwares. So with these thoughts, these in my department got often discussed. When we had the algorithmic advantage, we thought to create, and it's fluid dynamics, we wanted to have a more detailed tool, high fidelity tool. So Professor Narasimha, one senior professor in our department, kind of suggested, or we preferred from his article, and we discussed with him and got it, a slogan called Drik Ganit Aikya. And that I thought is fitting very well with the fluid dynamics, turbulence computing aim, that you want to resolve all possible scales. And what Drik Ganit Aikya, which was used in all Indian mathematical literature, is Drik means to see, Ganita is to compute. So it's extreme computational positivism, that what you see is what you compute, that both are same. And that would be the aim of a direct numerical simulation, that you take a physical system, you know the equation of motion, use it to predict what is the outcome you will get. Based on this, the startup has created lots of tools, so which we name in the same tradition. We call our platform as Vivid. Fluid dynamics tool is Taral. Agni is a heat transfer tool. Rangoli is our multi-component fluid tool. Kanad was an Indian scientist in the olden days who proposed the atom idea. So we call particle system as Kanad, and our interface as a Munch. Where would we need new tools when we said that there are software companies who have monopoly? So as it happened in science and engineering, whenever there is a technology change, so what is happening is computers are becoming way more powerful. There are better algorithms. And that provides opportunities for more direct simulation, more high fidelity simulations. For example, in a more technical term, aircraft stall is one area where conventional RANS tool don't work. Aeroacoustic noise, here for example I have shown example of aircraft, this bay from where another object is launched. Typical Renault number would be in few millions, and you would like to compute the interaction of flow with acoustic, and that has a structural consequences, and that's the reason engineers would like to compute it. And so here you need more high fidelity tools, and the hope is with the increase in compute power and algorithms you will be able to do, and that means everyone is at the same footing. So everyone would need a new set of codes. Most of the commercial tools are RANs, so you need commercial tools which are working on a direct numerical simulation or Ganitaikya or LAS, and that's where we work. The other part is lots of engineering design in general is changing towards the idea of digital twin, and here I'm not using digital twin in the sense of machine learning. What I'm using is that given any physical process, you have a model of it on computer. For example, if you are designing new carbon capturing technology or any energy technology, even 1% saving you get by a better computer design. And traditionally, these were done experimentally, that you do something in the lab and then do the tenfold increase, and that's how chemical engineering work, that every time you scale it by a factor 10. Lots of these things are moving to direct numerical simulations. So can we develop codes which will do these kind of processes? And it's apt that 2021 Nobel Prize was given in the science of complexity. So essentially, engineering design and simulations are moving towards complex systems. Can we have tools which are also up to that? So this example I already showed. And by the way, this is our own simulations done with our own tool, both of this. Here I'm showing a coal gasification plant, essentially to generate electricity via syngas. So this is a direct numerical simulation, so where you'll have particles, reactions, and all this. So you need complex models. So the idea would be you have a more detailed complex model, physics-based, which you use to understand the system better, and then use machine learning or any other neural network-based method for quick control of it, and use it for the actual physical system. So you have a digital twin. Another extreme example, which as a startup we work, is cardiovascular systems. So if we can do it for machines, we probably can do it for some of the biological systems also. So this is, initially we had a project at the JNCSR to develop India's first database on the coronary artery disease. So here what we were looking at, traditional, so what is known as a stable angina. Often people go to hospitals with chest pains which are not serious, but they feel uncomfortable, so they go to the doctor looks at the profile, there are rules of thumb, based on that they decide whether to do angiogram or angioplasty or not. Over period, people have understood that this process is not, these rules of thumbs are not so efficient. Quite a number of mistakes which happen there. So that's where this, in US there are a bunch of startups which started working on this with this kind of possible protocol, that when somebody goes with a stable angina, what you do is you generate the geometry with the CT scan, get the the coronary artery, voxelize 3D images, use this to predict what is the pressure drop across the blockage. And I remind that the blockage itself, which is often used in India, is not a functional criteria. What matters is the pressure drop. So one would like to know the pressure drop, and this can be done via the pressure sensors in the angiogram. So what we thought is to create a database of actual data, actual patient artery, where we put the pressure probes and measure the pressure difference. And that was a Karnataka government funded project via which we generated this database, which can be used by almost any group. So this can be used to test different fluid dynamics algorithms, whether you can predict You take the coronary artery, voxelize it, and then do the simulation on HPC clusters, and can you predict the pressure drops? Now, tools. What is our advantage? So I'll start with a little bit of history here. So as I showed you the random number tool, our philosophy is to use a simplified molecular description. So the same is often done in the fluid dynamics also. The first paper appeared in 1986. There was a lot of hooplas. So essential technical breakthrough was to understand that even at the discrete level, one can build a fluid kind of symmetry if one chooses the lattices appropriately. For example, in 2D on a hexagonal lattice, you can create a simple game, which Wolfram used to call as a cellular automata game, which has fluid-like symmetry, at least in approximate sense, to reproduce the fluid equation of motion. And that created a lot of excitement. Many people started telling that this might solve the problem of turbulence at the compute level. And here, a remark for students about the fads in science. Every 5 year or 10 year, we do see that this particular tool is going to solve all the problem. So for cellular automata, almost immediately newspapers declared that this is something so important that it should be restricted. That was a time of Cold War, 1989. So they said this tool should be out of Soviet hand. This can be used to design aircraft and other things. But in reality, so this slide I have taken from Professor Sorasuchi. So in reality, this algorithm has lots of drawback. It was extremely noisy, less accurate, and so on. So this was the first generation tool. Over period, lots of people were working on this tool. So what I will call lattice Boltzmann 1.0, a lot of people refined it, made it stable, made it a working algorithm. They had a set of lattices where you can compute the incompressible fluid dynamics in a very good way. But there were challenges here. Initially, these were thought as more a theoretical challenge that you are solving for distribution function. Distribution function is about probability density. Why probability density can go negative in these algorithms? Very fast, people realized that this has practical consequences also. If you don't respect second law in discrete system, you can get unstable algorithms. In initial days, lots of group, including us, worked on stabilizing this, building the second law of entropy into these algorithms. So that's one advantage. So we were deeply involved in these algorithms. So essential idea was the way you derive the equilibrium in the statistical physics, you do the same here. You start with a discrete H function, solve the discrete variational problem, and get a equilibrium which would be discrete analog. The theoretical issue here is Maxwell-Boltzmann emerge if particles from the isotropy of the fluid. So if the particle is allowed to move in every direction, isotropy and independence of different direction will lead to Maxwell-Boltzmann equilibrium. But when we are talking about discrete system, where particle is restricted on few direction, what equilibrium even mean? So essentially people managed to pose this as a variational problem and solved it. That gave another impetus that maybe we can do more. So then ideas started to get floated that maybe the time steps should be chosen in such a way that at every grid point, entropy should always increase. And that was also done more as a constructive procedure. I was lucky enough to be working on this as a PhD student. So we developed algorithms which would compute time step in such a way that second law is satisfied, and that worked. It was expensive, but it was a theoretically nice tool. Over last 5 to 6 years, in my group, we got a couple of real breakthroughs, I would say. So there was a PhD student, Atif. What he did is he actually solved this time step problem, which is essentially solving a highly nonlinear equation. So you have entropy, which is a nonlinear function of populations, and you want to get a time step which is essentially intersection of your derivative direction. So you are trying to find the path length for which you don't cross this convex surface. This is traditionally done. Such problems are traditionally, such search of intersection between convex surface and straight line is solved numerically. What this student did, he managed to find an analytical solution for this. And Chakradhar showed a lot of nice implementation of this to show that we can actually get huge number of advantages if you have conceptually this kind of algorithm. What we achieved is an explicit algorithm. So I remind that in numerical method, standard rule of thumb is if you want unconditionally stable schemes, you move to the implicit schemes. If you work with explicit schemes, it would be conditionally stable. That means time steps would be much, much smaller. Now what these students managed to create is an explicit tool which is essentially motivated from thermodynamics, which is explicit, so very easy to compute, but also stable. So it can work with a very large time step. And that both computationally as well as conceptually was a good progress. So this paper kind of describes this. And that's one advantage we had. The other advantage we had is we were looking at different kind of code, including the code we were working on. We saw one distinct pattern. There are two kinds of Pde solvers. One which works on a structured grid, one which works on unstructured grid. Unstructured grids are very, very efficient mathematically. So they are very accurate. You need a lot less point to compute something. Structured grids are very inefficient in terms of accuracy, but very efficient in terms of computer implementation. The reason is most of the PDEs are memory bound, not the compute bound. And we were essentially looking at this problem more from optimization of memory bound codes. So we had a bunch of algorithm how to optimize the memory bound codes. We created a bunch of data structure to do this, but then we immediately thought to pose this problem mathematically, why accuracy and bandwidth utilization has to go orthogonal to each other. Can we have structured grid? What a structured grid has an advantage that they are easier to implement, so computer compilers will be able to optimize it better. Can we have a structured grid which has performance like even approximately like an unstructured grid? So your first clue came to us that this is essentially a simple cubic grid, what we do in a structured grid. And if I think from the bandwidth limited function point of view, simple cubic is, so what we are doing in turbulence, we are saying that there is a cutoff scale, Kolmogorov length scale, and there are no wave numbers beyond that, or it's not relevant. It's so dissipative that it's not relevant. So that will be mathematically like a bandwidth limited function. So essentially you are trying to model a sphere in Fourier domain. Now when you take a simple cubic grid, Fourier transform of it would be also a simple cubic grid. So you are taking a sphere and mapping it to a cube. So there are lots of vestas of the Fourier mode. If we look at the problem from this point of view, the solution is obvious, that move to the BCC grid. What happened? Sorry. Something happened. I'm sorry, this is frozen. The screen is frozen. Even this is not working. What happened? Oh.
Yours?
Yeah. Yeah, probably. Standard Microsoft problem. I'm sorry about this. Point of view, sorry for that interruption. So once we think from bandwidth limited function point of view, it's obvious that one should use the BCC grid. And this is something well known in the computer graphics community. And here what I'm showing is what we will be often interested in, looking at the interface between fluid and solid. So you want to resolve different objects. So with the same number of grid point, how a simple cubic grid will resolve and how a body center cubic grid will resolve. That can be also understood just from looking at the image, that on a body center cubic grid, you approximately double the number of cuts at the boundary without actually increasing the grid point by a factor 8. You only increase it by a factor 2. So you save in terms of grid point by a factor 4 compared to the simple cubic grid. And again, because delta t is proportional to delta x, you save another factor 2 there. So it's almost one order of magnitude better. So this was done by this PhD student Manyusha and another student Praveen. So based on these kind of ideas, we had a distinct advantage, and that's we use to build our code. So to summarize, we had these advantages. We had a set of Pde solvers which work on BCC grid, which we felt is much more efficient. We have a set of fluid dynamics solver where you don't have to put any empirical model. Thermodynamics will decide your time step and you will get unconditional stability. And there are a bunch of other algorithmic advantages. For example, Some of them are described in this. Based on this, we decided to build this code which formed the bulk of Sankhya Sutra. So I'll just show now a couple of examples before I end. So this is, for example, one of the first success we had to do the stall simulation. So we looked at the aircraft at a certain angle of attack, or sorry, aerofoil, and looked at the CP and whether we can predict the flow separation. This worked quite nicely. So Atip did this in this walk in VRL. Based on these tools, our first commercial project, what we got, was essentially related to equipment in CVD process. So where you take lots of multi-physics, put them together to solve an engineering optimization problem. So what is important here is just that you need a code which is solving heat conduction, which is solving turbulence, which is solving rarefied gas flow, and also electromagnetic solver for Joule heating. We put it together to solve a particular engineering problem for this industry. So that allowed us to keep going. Now we can do these kind of, with our code, we can solve actually this kind of problem. So for this so-called open cavity problem, this is a simulation at 6.7 million, which is supposed to be extremely hard, and Mach around 0.85. And we can actually predict both pressure as well as the sound level at the different probe points. What experiment predicts and what simulation predicts are pretty close to each other for almost all probe points. And it's much more efficient. Traditionally, one writes separate solver for acoustic and separate solver for the flow. In this case, both are same, so another efficiency. We participated in drag workshop. So this is a new design of car which was given to almost every court, and were asked to predict the CPN drag coefficient when nobody would have a prior idea about this geometry. So what we saw is our code was among, I would say, very good, if not best, in predicting CP and CD in this competition. An essential reason was we don't have models to tune the thing. So it's a direct numerical simulation in that sense, although the resolution is not good, so it would fall under LES regime, but there are no empirical power parameters, and what comes out of the simulation, you take it. This thermodynamic based approach seems to be doing good job here. Downside is it's computationally much more expensive. So the uses is much better for acoustic, separated flow, and so on. It doesn't have that low cost attached with the RANs. Now we could take shot at more complex problems. So for example, this is another problem we were dealing with of gasification. So here it's a very large reactor from where one end you inject the coal particle, and here you have pet coke and water mixture and essentially oxygen, and the output would be syngas and fine particles, and you want to predict this. So you want a code which can do this, and as these particles are moving up, they are also reacting. So the particle will start reducing in size, so your particle code should also take care of that complication. At the physics level, if you want to do it at a full glory, it would require close to 10 billion particles, 1.8 billion mesh. It's a 16 species chemistry, and all stiff react, or at least a few of them quite stiff. So these are the kind of complex problem one would encounter more and more often in engineering design. Here I'm showing our solver, of course not for this detail, but for reasonable accuracy, what we can do here. So here I'm showing the temperature field in this. So approximately 10-meter reactor. You are trying to solve with a resolution of few mm to few centimeter. And you have particle code coupled with the reaction code, coupled with the flow code. We could actually probe all this different, what happens to different component in this system. So in that sense, I would say we have a digital twin code for this system. Again, downside is still it's very expensive. For 10 seconds of physical time, probably it takes few weeks to compute it on this large cluster. But as computing improves, these kind of codes will become more and more regular, and one would use such complex code more and more often. And this is essentially what we are trying to do at Sankhya. Now, we can actually do this virtual angiogram with our own tool. So this is the level of voxelization we can do. So we get the CT scan. We have our tool to create the 3D geometry. We can look at pressure drop at the different things. So this is for one given patient geometry. The other challenge here is to do it at low cost. We are expecting that we can do it at a much lower cost. And this was headed by Professor Sundar from IIT Bombay when he was doing sabbatical in Sankhya. With this, I will end with this comment. So I hope I convinced that in that sense, there is no separation between fundamental research and applied research. And I don't believe that one should do purely fundamental or purely applied. I would end with this comment I found in a book, Why Do You Read Sri Aurobindo? Only. So what he said, I do what I like. So in the same way, many of us in science, we do what we like. And with this comment, I will stop. Thank you.
Yeah, thank you, Dr. Santosh. Very nice talk. We have time for a few questions. Yes, Rajdeep.
As you mentioned, yeah, thank you for your talk. As you mentioned that the very beginning, the random number generator, correctly that one generates uniform random number and then transforms to Gaussian or other, whereas you are able to bypass that and directly generate a pair of Gaussian numbers, I think.
And, we are getting a stream of, so generally we do 500 particle or 1000 particles.
Okay, fine. So if you could just tell, maybe I missed, what was the physical principle that allowed you to generate different distributions? That's what you gave the analogy of Maxwell's
so it's
demon.
essentially computational Maxwell demon, which is allowing you to compute. So if you take a bunch of particles at equilibrium, the velocity of the particle system, as long as they are satisfying the detail, as long as the interaction model between them is satisfying the detail balance, mass and momentum and energy conservation is satisfied, those particle system will equilibrate their velocity to Maxwell-Boltzmann.
Correct.
There are no external force, so the position will equilibrate to uniform distribution. If I look at the number density in a volume, that will give me Poissonian. That's the
Okay.
And if I look at what is a bit more technical is, if I take a plane and look at the energy across that plane, a two-dimensional plane, that would be satisfying the exponential distribution. And that's the physical principle we used.
Okay, so number density in a small volume. So
Yeah,
that it's
whatever, yeah. So,
because if the volume is big, again that Poisson will converge to Gaussian. Okay.
no, why Poisson will, because position is uniformly distributed.
Okay.
So it's the fluctuation you're looking at, so that will be.
Okay.
Yeah.
And the exponential is coming from the energy distribution.
Two-dimensional projection of an energy. That's the simplest thing we could think of.
Okay. Okay, thank you.
Hi Santosh, nice talk. On just continuation of what Rajdeep asked. So to this random number generator to start it, you need to run some MD background, right?
Yes.
To get the configuration, so it will have some lag time or startup time.
It would have a lag time, it would have a start time,
Right.
but it's more like a pipelining in computer
Okay.
codes.
Okay.
And the fact that you don't need a large number of particles
Right.
to build it is what allowing it to be practical.
Okay.
So we wrote it with different kind of molecular algorithm. We had a Leonard-Jones code, we had a hard sphere code. All of them are doing essentially the same thing.
Right.
One of the doubt we had was what will happen to the equilibrium correlation.
Right.
That is also nicely, so it very fast breaks the correlation. Efficiency wise, we zoomed into an algorithm called stochastic rotation or multi-particle collision dynamics, because it's very simple algorithm. So
Thanks. Check.
I had a follow-up question to that as well, and maybe this doesn't make sense. How many decimals do you have to keep track of before to get?
no, it does
the
make sense.
distribution?
That was the question even one of the reviewer asked.
Okay.
We don't see too much of sensitivity to that.
Okay.
I don't think that detail matter too much in this case.
I have a completely
Though
different question.
this answer might be controversial.
Okay, all right. Completely different question. You mentioned Professor Narasimha's take on the Needham question.
Yeah.
Maybe you can, now that we're in the question answer session, maybe you can tell us about your version or your answer for why.
So, well, my
modern
take
science-
is past. It doesn't matter. We should be proud of it, but what we should be more worried about is future. That if we don't build, again we will be talking in 50 years why we don't have advantage.
Hello?
Yeah.
Lattice Boltzmann involves a Galilean invariance problem you have mentioned.
Yeah.
That leads to some kind of a weird relationship of viscosity with velocity. So how do you solve that?
So essentially what you're asking was a relevant question for lattice automata. So when people moved from lattice automata to lattice Boltzmann, that's the first thing they solved. So the particular isotropy, they did it at the low Mach number limit. Now, I've not gone into that technical detail. BCC grid also had another advantage. So when you want to build Galilean invariance at higher and higher order, the standard way to build it in lattice Boltzmann is you take more and more link direction. So and for computational reason, you want link direction to be integer multiple of each other. So you take more velocities. People have gone up to 300 velocities and so on to go to high Mach number. What we thought is when you are working on a BCC grid, essentially you are getting another advantage that you are no longer restricted to integer multiple. You have rational number space available to you. And that essentially allow you to build much higher level of accuracy in Mach number, and that translate to Galilean invariance with much lower number of velocities. For example, we could do up to highest Mach number around 2, approximately around 2, with just 80 velocities. And technical reason is essentially we can throw in more. First BCC cell are more isotropic, then I can throw in more and I'm no longer restricted to integer ratios.
I have another question. What do you think? Is it the understanding of subgrid phenomena going to lead more breakthroughs or more efficient solvers?
I don't know. For example, one of the detail, I'm happy that, so one of the, we kept it initially as a trade secret. Recently, another group has published, so now I can talk about that part. Our codes are if you look at algorithms like LB, these are matrix-free algorithms. And matrix-free means, in principle, at least for a bunch of algorithms, you shouldn't get into precision problem easily. So you have an option, like machine learning, to throw in more grid points. So you compromise the precision, but get more degree of freedom. And that will give you more accuracy. So I feel both will work in parallel. So what is happening with these kind of computational trick, plus the cluster we have, now if you buy the cluster today, that would be already 3 times faster because the memory bandwidth has improved. So I would feel that within a couple of years, a 10-fold increase in, because of the algorithmic advantages, hardware advantages, you will get it. So I see that in few years, LES would be norm rather than exception. Now, that would help to get better theoretical understanding? Probably yes. And probably that will also feed in and create more better models. That, I don't know whether it answered.
It's focused around a situation whether the future investment in science should be more on understanding the physics or getting into only software.
Again, do we have such strict divisions? Compute will improve. You will start getting more and more accurate simulations at a cheaper and cheaper cost, better algorithms and all that. Won't that feed in better theoretical understanding too? For example, I feel, again, no theoretical basis, what I see it from computations, for many turbulent computation, what matters is your resolution of boundary layer. So that is RE power half scaling. So that would mean essentially my cost of computing is scaling like RE square. On the other hand, Kolmogorov theory will say it's REQ. I don't think that mathematically it's a very settled issue. What is the degree of freedom? Even this basic question, what is the degree of freedom in turbulence? So maybe the situation, compute will also allow you to get a better sort. Maybe the actual situation is something in between.
Are there any more questions for Dr. Santosh? Okay, maybe I can have the privilege of the last question. You talked about the stiffness, and basically the stiffness essentially comes because of time and spatial scales that you might encounter in the overall behavior. Could you give us an idea of, for example, in the gasification case, what is the difference in time scales that basically make the system stiff?
So there are some certain reactions which are very fast.
Okay.
Some reactions will happen even at the 10 power minus 10 scale second.
Okay.
On the other hand, if you are looking at the compressible code, so the fluid time scales would be of the order of few microseconds.
Okay. And so, if one were to actually solve this in real time, then one would probably...
Real time, I don't think that we are anywhere close to it.
Okay.
So again, it would have the engineering hacks that you solve what we were discussing yesterday, that you saw, you look at the detail solver, from that you generate a lower order models.
Okay. Thank you.
Thank you.
Okay. Thank you, Dr. Santosh, for this very nice, brilliant talk, helping us to look and understand at various scales and what is the complexity that can get introduced. Please join me in a round of applause for Dr. Santosh.
Thank you.
I would now like to request Dr. Rochesh Thaukar to kindly step up and give the memento to Dr. Santosh. Dr. Rochesh has been the anchor for the visit of Dr. Santosh, so maybe request you to please do the honors. Difficult to be formal with a friend. Thank you very much, Dr. Rochesh. Thank you, Dr. Santosh.
Thank you. Thank you, Professor. I can take this away now.
So I'm sure all of you would agree that this was a very nice talk by Dr. Santosh. It's my pleasant privilege to propose a vote of thanks to close this Institute Colloquium. At the outset, of course, I would like to express our sincere thanks to Dr. Santosh for his time this evening and for illuminating talk on various aspects of multi-scale phenomena and how we try to understand them. I would like to thank several entities who have helped in arranging this Institute Colloquium, beginning with the Institute Colloquium Committee itself, the PRO, the Public Relations Office, the Development Relations Foundation, the Dean ACR Office, and of course the Senior Administration at IIT Bombay. I would like to sincerely express our thanks to all of them. And finally to all of you for attending this talk this evening. I'm sure there are some very nice messages that all of us can take as we go back. I hope it was also very interesting to all of the PhD students who have been attending this talk. So thank you very much, and please join us for tea in the foyer. Thanks.